Hello viewers, I'm Kausalya. Today we are going to discuss about single tuned coupled circuits. So here this is the diagram of a single tuned coupled circuit. So here in this case the two circuits are said to be coupled, right? That is, the current flowing in one circuit will influence the another circuit, right? So they are said to be coupled. So here, in addition to that, they are said to be inductively coupled, right? Because here these two are the inductors. Only by means of these inductors these circuits are coupled, right? So here the coil 1, okay, this is your coil 1 and this is your coil 2. So here you see the coil 1 has a source voltage EG and there is a source resistance RG, right? And here there is a variable capacitor C. So since we are having a capacitor on only one coil, this is said to be a single tuned coupled circuit. If we have capacitors on both the coils, that is coil 1 and coil 2, then it is known as a double tuned coupled circuit, right? And as we all know, R1, R2 are the respective resistance of the coils and L1 and L2 are the inductance of the coils, right? And here this RG, this is nothing but this is your source resistance, right? So now we are going to apply KVL and we are going to frame expression. So when you apply KVL for your coil 1, what happens? I1 is the current that flows through this path, right? So here sum of voltage drop is equal to sum of voltage rise. So what are all the voltage drops here? That is, when you compare here, you see we are having I1 RG, right? Then the next thing is I1 R1 and the next thing is the voltage drop due to this inductor L1, right? And the next thing is finally there will be some mutual inductance. We have to include that also. That is, the drop due to that mutual inductance should be also considered, right? So here while writing expression, you see this is I1 RG plus I1 R1, right? And the next thing is plus I1, that is we have written I1 RG and this I1 R1, and the next thing is I1 into j omega L1, right? Then you see here the way of current entering the coil. You see here the current enters through this dot, okay, enters the inductor through this dot. But here in this case for the coil 2, the current leaves the coil through this dot, right? So they are opposite to each other. Therefore the mutual, that is the voltage drop due to mutual inductance is given by minus j omega m I2, because this is a voltage drop which is produced in your coil 1 due to the current that flows through the coil 2, okay, that is known as mutual inductance. So here which is equal to, here the source voltage is EG, so which is equal to EG here, right? So just for our simplification, here you see the value of RG is comparatively greater than R1, which is greater than your j omega L1. Therefore, here in this case, we are going to ignore this R1 as well as this j omega L1. So when you ignore, you see what happens? Our equation gets simplified like this. Right. Now we are going to write KVL for our coil 2. So here when you apply KVL, what are all the elements here? That is R2, there is L2 and there is a C, and apart from that there is a voltage drop due to mutual inductance, right? So the same way here while writing expression for mutual inductance, it is minus j omega m I1, because this mutual inductance is due to the current that flows in the coil 1, right? And the rest they as usual, that is I2 R2. So here you see I2 R2 plus j I2 into j omega L2, and here the voltage drop across this capacitance is given as I2 into minus j by omega C, right? So this is our expression for your coil number 2, right? So here these are all the two equations for our two coils. Now we are writing these equations in matrix form, right? So here the coefficient of I1 is Rg, here the coefficient of I2 is minus j omega m, right? Similarly, here the coefficient of I1 is minus j omega m and coefficient of I2 is all these things, right? So multiplied by I1, I2 which is equal to Eg, and here there is no source voltage in our coil 2, therefore it is 0, right? Now the next thing is we are going to find the del. Del is nothing but determinant of this matrix, right? So when you, this is your del, right? Just we are going to find out the determinant. So here now, once you find the determinant, you see this is the value of the determinant here, right? Now the next thing is del 2. So here del 2, in order to find del 2, we have to replace this column by this value. So when you replace it here, you see the value of del 2 is plus j omega m Eg, right? So now we are going to find I2. So I2 is nothing but del 2 by del. We know the value of del 2 as well as del, therefore just substitute it here. Right, so this is your expression for I2. Now the next thing is we are going to calculate the output voltage. So when you look back at the diagram, so here this is your E0, right? So E0 is nothing but this is your voltage drop across your capacitor, that is I2 into the respective reactance of the capacitor, right? Therefore, the output voltage E0 is given by I2 into minus j by omega c, right? So since I am bringing this j downwards, okay, here this minus becomes plus. Therefore, I2 by j omega c here. Now, we are going to substitute the values for E0 because we know the value of I2, right? So here, just substitute the values. So this is your expression for I2. Right, so just substitute this over here, and here this j omega cancels each other, and finally the expression for E0 is given by this value. Right, this is your expression for E0. The next thing is here we are going to find the ratio of output voltage to the input voltage, right? So here it is denoted by the letter A. So A is equal to E0 by Eg, right? So here we are having E0, right? So we are moving this Eg downwards, right? Output voltage by input voltage. Therefore, the value A is E0 by Eg. So the rest of the elements, they remain same, right? Now the next thing is we are moving to a condition known as resonant frequency. So resonant frequency is nothing but omega L will be equal to 1 by omega C. Or in other words, we can say XL is equal to XC. That is, inductive reactance is equal to capacitive reactance, right? So here in this case, XL is given by omega L2, right? Because since we are considering the elements on the coil 2, okay, elements of the coil 2. Therefore, omega L2 which is equal to 1 by omega C. Again, I am combining this omega together. So this becomes, when you move this omega to the left hand side, omega into omega becomes omega square. And I am moving this L2 to the right hand side and it occupies the denominator part. And finally, the value of omega is given by 1 by square root of L2 into C. Right. So here now we are going to apply this condition. That is, you see, this value is equal to this value. So one is with plus sign, another is with minus sign. What happened? They will cancel each other, right? So at resonant frequency, these two terms cancel each other and this expression gets modified like this, right? So here in this case, I have just multiplied this Rg with this R2. And here omega becomes omega R because this is under resonance condition, right? So omega R square into M square. Now we are going to find the value of I2 at resonance. So again we are going to apply the same condition, right? So in the expression for I2, again these two terms will cancel each other, and finally our expression for I2 looks like this, right? So here the output voltage, right? Output voltage, current and amplification, okay? This term A denotes the amplification. So A depends on the mutual inductance M at resonant frequency. That is, all these equation predominantly they contain the mutual inductance, right? Therefore, mutual inductance play a key role in determining these values, right? So here again, when M is equal to K into root of L1 into L2. Now, to get the condition for maximum output voltage, how to find the maximum output voltage? You have to differentiate this expression and you have to equate this to 0, right? So here again, dE naught by dM, that is your output voltage. I am going to differentiate this output voltage and equate that to 0 here. So again, the expression for E naught is, this is your expression for E naught under resonance condition, right? So now I am going to differentiate. So here the basic thing is, we are going to differentiate with respect to M, right? So when you look at this expression, we are having M on both the numerator as well as on the denominator, right? So it is of the form U by V. So here the expression is V square, right? When you differentiate, the formula is, it is nothing but V square V du minus U dV, right? Here this is your V. So V square, just square it. And next is V du. So this is your V, just write it as such. And when you differentiate this numerator part, M becomes 1 and simply Eg minus U dV. This is your U and dV. You have to differentiate this part. So here this term is constant, so it will become 0. When you differentiate this, here M square becomes 2M and the remaining terms remain as such, right? And now we are going to equate this to 0. So when you equate it to 0, what happens? For example, when you equate this to 0, 0 into this term becomes 0. So here we are considering the numerator now, right? So when you again, just I am moving this term to the right hand side so that this minus will become plus here, right? And since Eg is present in all the terms, I am dividing this equation by Eg. So here finally we are having an equation like this, right? So again, you see, the value of M square is easily calculated as R2 Rg by omega R square. Therefore, M is nothing but R2 into Rg by omega R, right? So, when the value of mutual inductance is this, then the value of output voltage is maximum, right? So, the maximum output voltage is, again we are just substituting the values. In the place of M, we have substituted the values. So, when you substitute the values and solve, finally we are ending up with an expression like this: Eg divided by 2 omega Rc into square root of R2 into Rg, right? Now the next thing is amplification. So here the maximum amplification is given by, that is output voltage by source voltage, that is E naught maximum, right? So here this is your expression. So just substitute it and finally we are getting the value of AM as like this, right? And the maximum value of current, again in the place of M we are substituting the value, right? So M is replaced by square root of R2 Rg by omega R, right? So just substitute it, and once you solve here, the maximum value of current is given by this expression, that is Eg by 2 into square root of R2 into Rg, right? So here comes the end of this video. If you have any doubt, let me know in the comment section. Thank you.